I'm going to give you a very brief welcome and thank you for coming. My primary job is to introduce the director of the Boulder Summer School, Professor Leo Radzahovsky.
Good evening. Wow, it's really amazing with this overwhelming rain to still see so many science enthusiasts or maybe cooking enthusiasts still show up. This speaks highly of Boulder. So welcome. It's my pleasure to host this event and to welcome you here and to introduce tonight's speaker. But before I do that, I wanted to give you some background to what this event is all about and how it relates to what's going on in the physics department in July. So this public lecture series is part of what we call a Boulder Summer School for Condensed Matter Materials Physics, which is held here every year for the past 12 years. This is the 12th Boulder Summer School that we have here. And what it involves is we invite around 65 best and brightest science students from all over the world. So best and brightest, maybe raise your hands. If you need some clarification, you can about the lecture, you can turn to your side and see if one of the best and brightest are next to you. Anyway, we invite about 65 best and brightest international students from all over the world to come and get lectured for about 4 weeks in July by some of the world experts in the field of the school. And every year the topic of the school changes. So we've had 12 schools, and these schools have ranged on a diverse set of topics, ranging from superconductivity to biophysics, magnetism, polymers, glasses, and all kinds of topics. This year's school is on hydrodynamics, and this is a subject quite old, but it's still in many ways at that frontier of theoretical physics, mechanical engineering, chemical physics, chemical engineering department. And what it's essentially, for the non-experts in the audience, it's really a study of fluids, or fluid-like states of matter, and it can range all the way from simple-like fluids like water to more complicated suspensions like paint or mayonnaise, if you wish. Some of the people hear from Michael. So the school is supported, the Boulder Summer School, this Institute, Advanced Studies, is supported by National Science Foundation, and we're very grateful for their support for the last 12 years, and hopefully will continue. And so this public lecture is part of that, and so really this is a small example of your valuable tax dollars at work. There's much more behind the scenes that bring you iPods and CDs and iPhones. So tonight's lecture will be given by Professor Michael Brenner from Harvard University. He's one of the world experts in the subject of hydrodynamics, and of course needs no introduction to people who do study that subject. He's well known for many imaginative and very diverse set of contributions to this field. He's really quite unique because he's also extremely well known for his kind of down-to-earth, easy style, very pedagogical exposition to the subject, as you will see tonight. Pressure's on. Just to give you some taste of what Michael is like, just the other night at the fireworks, I was mesmerized by the pretty lights and kind of just interrupted once in a while by agonizing of how many things I have to do the following morning. Michael, having not finished his lectures, was busy constructing theories of the fireworks, what the shapes are like and how big they are, and then he proceeded to incorporate that hokey theory into his lecture the following morning. He really does have eclectic tastes in science, and that's exemplified by the title of his tonight's lecture. Michael was got his PhD at the University of Chicago in the mid-90s, and that's where I had the first pleasure of meeting him at the postdoc there. Soon after, he was moved to MIT as a professor in applied mathematics, and within a few years, he was lured away by another institution down the street, like Harvard, where he's now a global professor of applied mathematics and applied physics. So, without further ado, please join me in welcoming Michael.
This might work. thank you for that introduction, Leo. You oversold that massively, as you're about to see. Okay, so let's see. So I'm going to talk tonight is titled Science and Cooking. And I guess in the interest of scholarship, I have very many scholarly colleagues around who are very interested in old quotations, and I thought that it would be worthwhile to start with one for all of you. So this is a quotation from a great French scientist named Brenner, who in the early 1800s wrote what I think, although I'm not 100% sure, is the first serious scientific study of the science of cooking, and it's called The Physiology of Taste. And it's a wonderful book that I recommend to all of you. It's online for free, and it's beautifully written. It has wonderful sentences in it. The one that I like the best is this, namely, the discovery of a new dish confers more happiness on humanity than the discovery of a new star. And I thought this was appropriate for tonight because probably you guys have had, oh no, it's condensed matter physics, but I was going to say probably have had public lectures on stars.
Absolutely.
Yeah, but what about new dishes? So today we're trying to fill in that gap. So, okay. So, science and cooking. So I have to, so this slide is a slide that's supposed to remind me to apologize to you for several things, which I should just get out into the open at the very beginning. So the first thing is that I don't know how to cook. And so I learned, so everything I know about this subject, I've learned over the past year when teaching with my colleagues, and I'll describe this to you throughout this lecture, our course, an undergraduate course that was really designed for history majors. It was what is called a general education course at Harvard on science and cooking. And so what I'm going to do tonight, the way that this thing is structured, is I'm going to tell you about the course. And the course is partly because I like this story and I'm still getting over it. This is part of my rehabilitation from the course to talk about it. And so you guys are going to have to listen. But it's also, it was our effort to put in a somewhat pedagogical way the main scientific ideas in cooking. So while this will be, a lot of this will be about the course, there will be science interspersed, and indeed we will do some cooking, and hopefully it will go well, and we'll see how that goes. So this picture actually, to me, sort of typifies the course. So this is actually, the students in this course, as I will tell you, every week have a lab. This was a course with science lab. This was, the English majors requirement, this is how they got out of physical science requirement. And every week, and we had a lab, we were fortunate to have a lab in which the students could eat the food that they created, and they made measurements on it. And this is a student writing up their lab report after cooking ceviche next to a Bunsen burner. And so anyway, this is the story that I'm going to tell you, and as we go through, I'll hopefully convince you all that there really is an enormous amount of science in cooking. It's actually quite related to both the topic of the school that's happening, and also really to a pocket of significant expertise in the physics department here, namely soft condensed matter physics. And so it's, and I guess this is something that I learned throughout this semester we're teaching it, and hopefully I'll convince all of you. And by the way, if I don't make sense, then interrupt me, and if you're bored, then it's okay if you leave. So I want to start with this slide. So this is just to emphasize at the very beginning that what the story I'm about to tell you required an enormous amount of work from a really large team of people. So this was a crazy idea that sort of gave way to my colleague in engineering and physics at Harvard, and two postdocs, namely Robot and Roger Campos, invented in some strange way that I'll describe to you. And it was a crazy idea, and we sort of started really in earnest preparing the substance of it last summer. It was essentially a year ago. It was a little more than a year ago today. And the only way that we were able to pull this off at any level was because of just the enormously hard work of a huge group of people. And I just want to emphasize that although their names aren't going to be on this, and if you imagine, well, hopefully you'll see why. But this is really, so I'm being spokesman. Okay, so I'm going to tell you how this happened. That's how that is the soft condensed matter physicists at Harvard got into this. So OJ, actually, who was a postdoc, had this crazy idea that we should invite Ferran Adria, who some of you may know, who was really, arguably the most famous chef in the world, to come and give a lecture at Harvard. And so OJ went to Dave and said, I want to invite Ferran. Dave said, well, there's no way he'll come, but sure, go for it. And so OJ invited him, and he then came, and he then gave a lecture that had the same title, actually, as my lecture. His lecture was in Catalan, so it was a little different. And also he's a chef, he knows how to cook. So, but anyway, so the lecture was absolutely mobbed. We had no idea. It was a lecture room about this size. The lecture started at 6:30. The room started filling up at 3:30. By 4:30, we had to get an overflow room. By 5:30, the overflow room was filled. And then there were literally hundreds of people in the hallway that were furious that they didn't get in, because he really is this guy's. So anyway, so this happened. And then it turns out the same day, we had a faculty meeting in which the people at Harvard who run what Harvard calls the Program of general education, which is the idea that everyone should take a science class. Let's just present it to you. It's also every scientist should take a history class. So they came and yelled at us that we weren't contributing enough to general education at Harvard, and we should have done more classes. So then the next morning we had a meeting with Farron and just to talk about, and he said, we really want to find a way to work together. And so I opened my mouth and said, well, it's a university, so we should teach a course. And he loved the idea. He thought, this is fabulous, I'll teach a course. Now, of course, he's a very busy person. His restaurant, El Bulli, is actually about to close. In fact, I think it closes the last day of July. So anyway, more on that later. So, but he's really a very busy person. So what he then did was he put his foundation, which is called the Alicia Foundation, to work. And they, with his endorsement, recruited 12 of the most famous chefs in the world to agree to come and to help us put on the science class. And so that was sort of the catalyst for this. And our challenge was, and this is really where the science comes in, so this is the background. The challenge was, how does one build a science class with real science where the students really learn? This is not, around that. This is what I'm going to describe to you, and in the process I hope to convince you that many of the foods that you eat and that you enjoy really, there's science in it every day. And actually, science and cooking really, I think, have a lot to do with each other. And so this was a science class, and I just want to, so the idea was to use these fancy chefs as inspiration, and so this is also partly a lecture. I'm sorry, this is a bit scattered, but this is also partly a lecture, at least for me, about science pedagogy. And this actually is also very appropriate to be given here because this is one of the world centers in science pedagogy. And but at least for me, that is the well, you'll see. That is because of the fact that so many people are interested in food. I mean, I just had the impression that we were able to communicate things that we never, under ordinary circumstances, would be able to do. So, okay. So I'm going to tell you, so basically the way the class worked was that every week, on Thursdays we had a science lecture. On Tuesdays we had another half-hour science lecture. And then from 1:30 to 2:30 we had a lecture from a world-renowned chef who was illustrating the concept of the week, and I will go through them. And this is really partly to tell you about this, but partly to sort of explain where science comes up. We then had a lab. Every lab had in it a recipe of the week, so every week there was a recipe. The students made the recipes, and they then made measurements on the recipes. This is a science lab where there were microscopes and things like that. And then every week we also, because it really was a science class, we had an equation of the week. And so we had one equation every week, and that equation was designed to illustrate the scientific theme of the week. And the students had to learn how to use the equation, and I'll tell you more about that as we go on. So there will be equations in this talk, I apologize, but only one per topic. Okay, so this was the lab. We were really sort of proud of this. So, it was a science lab, and then the drawers were made with thermocouples, cutting boards, and shakers. Okay, so now I'm just going to go through quickly. This is sort of more, so in May, actually starting May last year, we started developing the course with a group of teaching fellows, and so we basically, we had to invent labs, lectures, homeworks, everything measured. So this is Jen, who was a physics graduate student, who was basically in July, actually about a year ago, was putting Jell-O in pineapple juice. Actually, if no one knows why she was doing this, we can talk about that at the end. It's actually very interesting, that experiment. So then the local restaurants also got involved. They were so interested in the fancy chefs that basically they would volunteer their kitchens, because we, of course, had no place to test the labs. So we would have lab testing parties at local restaurant kitchens where the chefs would basically help design the recipes. We had boot camps where all of the students from the TFs would get together, the teaching assistants, and test all the labs. This was sort of the highlight of the summer. The core teaching fellows who basically really developed the lab, they made a field trip to WD50 in New York City, which is Wiley Dufresne's restaurant, and Wiley taught them how to make shrimp noodles, which became lab number 7. Okay, so then the class begins. So I have to put this in a little bit of perspective. This is partly, as I said, sort of healing for me. So I actually was teaching at the same time a math class, because I actually teach. So I was teaching a graduate math class, which is the one that John somewhere back there was the teaching fellow who really taught the class, actually, because I didn't have any time to teach it. And I ran 10 minutes early, as John will attest, from the class, because I knew I had to go to this next class, to teach this next class. And I ran to the Science Center, which is a building at Harvard, which is a lot like this one, that has a big lobby, big lecture hall off of it. And I was shocked when I got there to see the following. So this is a video that was made from one of the students in the class. I didn't understand what was happening, and then I realized that they were all there to get into this class. So then, let's try to get into the class. I mean, so I, well, there are some seats. I don't know. I'm not exactly sure sure what you're supposed to do in a situation like this. There are some seats a little bit further. If some of you could move out, more people will get. Notice that as in this lecture hall, there were hot pans that were there. I actually didn't think about the fire hazard at the time. I'll show you that. Okay, so then actually on the first day, I sort of pointed out, so actually then the history was that, we limited the enrollment in the class to 300. This was actually done as an afterthought at the last minute. I never actually, in my wildest dreams, thought people would come. 300 was chosen because we calculated the maximum number of people we could get into the labs. Because there was a lab every week, there was 2 hours. And so they then, the Harvard Law, so it turns out 700 people signed up to get into this class. And so I told the students on the first day, they were all very upset about this. There was a lot of them. The odds of getting into the class was 44%. The odds of getting into Harvard was about 10%. But the odds of getting a reservation at Oberlin, it turns out, is not. So then, I mean, just to show you, so I hope you don't mind this, so then the Harvard student newspaper is called The Crimson, and they then made this movie.
Why did you decide to shop science and cooking? I'm a freshman and I heard about this, I think even before I applied. I need the fun in it. I you applied at Harvard? There were many other reasons.
It's something different, and it's something that's like common, like cooking and stuff like that. It's like something fun, but it's related to something that's usually possibly boring, like physics.
What was your
I came on time, like not Harvard time, like on time, and I was all the way in the back.
Because the first day that I tried to go to class, I got like suffocated and trampled.
The line was ridiculous for like just shopping it.
All the way out the door. Huge long line.
And it's just like a total mob outside.
And I just didn't think there was any chance I was going to get in.
How hard was it to get in? Well, I didn't get in. Did you know anything about it?
Yeah, I had friends that made it through. They stuck it out, so they sat in on Physics 15 before class.
It's a hard physics class.
What are you looking forward to the most?
The labs, I think.
I think the fact that you can eat your lab is pretty much the coolest thing ever.
Like it gives them a way to actually understand science in a more complicated way, but
Okay, anyway, so okay, then the class started. So now I'm going to use this. So I'm going to tell you how the class went, and as such, I'm going to give you our outline, basically, of sort of scientific principles in cooking, which we'll then start to talk about a little more detail as we go on. And then actually, I should say, this lecture has 3 parts. There's this part, which I outlined. There's the second part where I'm actually going to try to cook, and I'm going to need volunteers to help me do some things because I can't really do this. And then the third part, I'm going to talk, and this may go over, in which case I'll just stop if you don't want to hear this. I'm going to talk a little bit about assessment, and sort of how does one, because this really was, and actually, I think the real value of this is possibly as a way of teaching science. So talk a little about that. So that's the deal. So okay, this is the first day. The first week, so there was the intro that I told you about. The first lecture, actually, we had 3 people. We had Harold McGee, who is probably the preeminent food scientist in the United States. He wrote a remarkable book called On Food and Cooking that I will tell you about. But if any of you are interested in science and cooking, it was actually our textbook for the class. This is the thing to read. It's got everything you want to know. It's a fabulous book. And we had Farron, and we had Jose Andres. And this was the 3 of them sitting there. And actually, what was interesting about this is that we were all excited about this, but they were excited about this too. Actually, and the reason, actually, I'll tell you. So Farron said to me at some point, and because I didn't understand this, why the chefs were so interested in this, and he said to me at some point, major universities have schools of architecture. There are schools of art, but there's no cooking. There's food science, of course, but that's different. That's really more about food safety. That's different than the science of why the food that you eat is the way that it is. It's a very different subject. And so, anyway.
I can't tell you how amazing it is to be standing here today. I'll try to explain, but it's going to be hard to explain. I wrote on food and cooking essentially in this building with you. I never in my wildest dreams thought that Harvard would ever teach a course in the science of cooking, to say nothing of my book, the book that I was writing then, being used as the textbook in that course. So this is completely mind-blowing.
Okay, and then there's Farron. So here's Farron.
15 years. We can all look back and say that we were here together on a very important day.
There were challenges in this class.
The day that an important relationship that began between universities and gastronomy, cuisine. because within 15 years this may very well be quite normal.
Era muy extraño.
It would be quite strange.
Okay, so then these guys had fun together cooking. They made something which is called spherification. How many of you know what spherification is? Does anybody? Some of you know. Okay, I'm going to show you. It's actually amazing. But anyway, okay. So then the second week we started science. So now I'm going to start talking. So the first topic that we discussed was called phases of matter. And this was the idea that matter has three phases. Liquid, solid, and gas. And as demonstration of this, and so we taught the students about phase changes, and phase diagrams. And as demonstrations for this, we had Johan Roca, who runs a restaurant that I think is ranked like 4 in the world or something. And he came in and basically moved the students through phase diagrams and showed them how food worked. So in the second week, which was where the course started, where really we started substance, the course started several important traditions that I'm going to subject you to right now today, if you don't mind. So the first tradition was that every week there was an equation of the week. I told you this already. And the rule was that whenever the equation of the week was presented, everyone had to clap. So I'm going to show you the equation of the week. Just to get into this, you're going to have an absolute clap. And the other one was whenever anyone presented an amazing dessert, you also have to clap. And so I'm going to show you the first 2 examples of this that occurred. These must be equal. It must be the case where motion and sticking are an exact balance. That's our equation of the week. Okay, so then here's our first amazing dessert. So watch this. The resolution on this isn't, but
Flor de gel fem fet de lacos,
Snowflake,
aquest meló gelat.
the frozen melon,
I aquesta és l'aigua, que està líquida encara,
and this is the water still in liquid state.
però quan cau a sobre el meló congelat es congela. Això ho fem a la taula,
And the reason was that every scientist in the room, if you turn to the scientist next, you can tell you how that happens, how you can take water and pour it and make it solid. And the reason is because water can actually be cooled below the freezing temperature. It can be so-called supercooled. Actually, David talked about that today. Actually, in our conference, he talked about supercooled water in rainstorms. Actually, we just had a rainstorm. So that's actually, but I know of no context, I know of no context where 300 students would be interested in physics or supercooling, but at this moment, every one of them was interested in physics or supercooling. And they all wanted to do it. And they all discovered, actually, it was very hard to do, but this is a different thing. So, but there are reasons for this, that every scientist, if you turn to the scientist next to you and ask why is it hard to do, they'll explain to you. And, but you see, now you're all of a sudden doing science. Okay. So the recipe of the week was 4-minute custards. We had pressure cooking, because we had to move around phase diagrams. So this custard made in 4 minutes. We also cooked eggs. Now, let's start talking about eggs. So so when you cook eggs, you usually cook them, if you hard boil them, you cook them in boiling water. And the reason that you do that is because water boils at 100 degrees centigrade at least. Well, not here, I guess, but in Boston. But on the other hand, you know what the temperature is. It's like a thermometer. But if you ask it, what temperature does an egg actually cook? It's actually far below 100 degrees C. It's at about 65 degrees C is where it cooks. And so we had a constant temperature heat bath in the lab. And the students actually cooked eggs as a function of temperature and measured exactly where the critical transition occurred. We also gave them homework. So here's an example of a homework. Here is the phase diagram for water. In lab, we cook custard and observe the difference in cooking time between the pressure cooker and the steamer. Use the phase diagram to rationalize this difference. This was actually the easiest problem. We also asked them questions like we gave them a recipe, and I literally almost asked them, so suppose you were going to do this in Boulder, how would you change it? And why? Okay, here's another one. In lab, inspected eggs. Please make a phase diagram for eggs. So please say where we talked about the physics of this later. So then the second week, Jose Andres came back. He talked about basic food components. We talked about proteins, fats, and carbohydrates. And the recipe of the week was ceviche, and I already showed you this picture, which I like very much. The experiment that we did, so how is ceviche? Has anyone eaten ceviche? So you can ask, how is cooking ceviche a science experiment? So usually when you cook ceviche, well, I don't know how you cook it. Most people use lemon juice. Okay, so ceviche is cooking fish in an acid. So it turns out that you can cook fish without heating it by putting it in acid. So we measured the critical pH at which ceviche cooked. That's what we did. We had all types of juices at different pHs. We had pH meters, and we had the students please measure, cook the fish, and then say where the phase diagram came as a function of pH. And then later in the course, I'm not going to tell you this, we actually tried to predict the physics of the transition. Then we did viscosity and elasticity. This is actually very related to the topic of this workshop. Viscosity is how easily a material flows. Elasticity is how soft it is. The lecture was given by Carlos Pejador, who was about olive oil and viscosity. And this was the recipe of the week. Fruit jellies. How is it science? So they measured the elasticity of that as a function of the concentration of pectin that was basically put in the thing. We also in class did this amazing thing, I thought it was amazing, is that we cooked a steak. We cooked a steak in class, but you know what we did? A steak. It has a steak. We measured the elasticity by pushing on it. So I know there's this thumb test that cooks use to decide if I cook it. So we measured the elasticity before, then we cooked it. We measured the elasticity after. And then we asked, what is the molecular, what is the reason that the elasticity increases what it does? And there are really two reasons, as the scientists around can tell you. One reason is that the bonds strengthen when you cook it, that's sort of holding the steak together. The other reason is that it expels light. And we measured in class that about half of the increase in elasticity was due to one effect and half due to the other. We then went on to heating, cooling, and tempering. That week we had a great chocolatier, Enrique Rivera. The recipe of the week that week was molten chocolate cake. This was by far the favorite recipe of the students. This was the demo that I got to do in class. So as I said, I couldn't cook, but there's this wonderful, the people that helped this course were amazing. And I got to cook a cheesecake. So I cooked the cheesecake. This is me cooking a cheesecake. And then this was the equation. Oh, you caught the equation. You guys are good. And then what we did, we put a thermocouple in it. We measured the temperature going up as a function of time during the class. It went up. And we then explained the physics of this during the class. We then told them, and this is something that I don't actually have time really to do here in detail, but I'll tell you that the physics of this is due to a molecular process called diffusion. And there's a fundamental property of matter that determines how fast the diffusion of heat happens. Diffusion is essentially the idea that when heat moves into, I'm going to heat things in a little while. When heat moves into it, it doesn't walk in like this. What it does is it does this. It sort of does this. That's what diffusion is. So, and there's a constant that quantifies how strong the dance is. It's called the heat diffusion constant. And we took this curve in class and measured the heat diffusion constant of water, as it turns out, within 10% from that curve. So actually, maybe I should cook something. I'm getting a little bored. Although now we go out of order if I cook something. I might ruin that again. I'm going to do this in a little while. So for you guys, I'm going to cook a tuna steak. So the good thing about cooking tuna is that, when you cook tuna, it goes from pink to white. And we're going to measure, right now, the heat diffusion constant of water by basically measuring the thickness of the white layer of the tuna. And I'm going to show you how that works. But we have to wait because I need the pans for something else first. And I can't put the tuna on them, otherwise I'll get messed up. So here was our lab. So actually, we ran a version of this, a 2-lecture version of this for the Harvard Alumni Association in May. And we gave them the lab. And the lab was molten chocolate cake. We also actually sort of went crazy and made ice cream too, because Amy and I were working all the time on this, and we then at some point decided, well, we're teaching about heating, but actually the principles of cooling are the same as heating, so we should demonstrate that. So therefore we went out and bought 10 ice cream makers, and the students made ice cream. But then it wasn't enough to make only normal ice cream, because that was a fixed temperature. So then we got vats of liquid nitrogen, and the students also made liquid nitrogen ice cream, and we measured the rate. And we sort of, this was, you can, anyway. So this was the students. These are the chocolate cakes, they're molten chocolate cakes. That was them taking a picture of their liquid nitrogen ice cream. They were very happy. We then gave them homework, draw a sketch of the temperature distribution inside the chocolate cake as you bake it. And then Enrique actually put on the chocolate demonstration for the students in the lab. He made a house. The Harvard Alumni Association did the lab. So what was amazing about this is that, so we gave them the lab. And then they were told to please summarize their observations. So, if you cook a molten chocolate cake, the interesting thing about it is that the middle is liquid. That's why it's molten. So there's a crust. So we told them to please measure the minimum and maximum thickness of the crust as a function of the time that they baked the cake. And then they were told to enter it into a Google Doc or a Google spreadsheet, a Google poll. And then I took all of the data from all of the alumni and I averaged it. And I was able to measure the heat diffusion constant of water with 10%. These are two of the alumni who were so happy they sent me their pictures. This was their chocolate cake. These were their measurements. And their number, so this was their number for the heat diffusion constant of water. Actually, it's 1.5 times 10 to the 9, so they were off by just a little bit. It's not bad, actually, given that Okay, so then we went on to protein folding and unfolding. Grant Achatz from Alinea in Chicago came. The recipe was homemade Chicago cheese. We basically talked about the physics of cheese. Cheese is fascinating, actually, making cheese. The students made cheese. They studied milk under the microscope. They did things like this. There are all these things you can do. We then went on to foams and emulsions, something that we'll talk about in a little while. We had a chef from Spain come who, in front of the students, made 15 emulsions in an hour and 20 minutes. Every one of the emulsions we put under a microscope and looked at them. And we'll do a little bit about that here in a little bit. They were all happy. These are Nando's emulsions. This is Dave giving Nando a gift. Then Jose came back. We talked about gelation. The students gelled something. I'll tell you what that is in a little while. We then talked about complex phase changes. We had Wiley come and talk about what meat glue. Students made shrimp noodles and caramels. Darren Barber came and talked about microbes and microbial science, and then the students did final projects. Okay, and then finally the last thing that happened is that Bill Yossi, who's the White House pastry chef, came, and he basically cooked also lots of his recipes and put them all into the microscope. And we have a picture of Bill, which I actually should have gotten to put in this thing, taking a picture of his recipes on the projector with his iPhone camera. And then actually, I got to give a lecture on the science of candy, which this is one of these things that could go on forever. That is, it's unbelievable how much physics there is in candy. Essentially, for those of you who are scientists, essentially all of material science can be done with candy. And it's amazing. You know, you want glasses, you know? I mean, you know, anyway. Okay, so now we're going to do a little bit of science. Or in a little bit of cooking. So let's see how this works. So I don't know if this is going to work, so you guys have to be patient with me. Okay, so I'll turn on the lights. Okay, so first, actually, I have some slides. What is cooking? Blah, blah. Okay. No, actually, that was important. So, okay, so if you look up in the Oxford English Dictionary, what is cooking? What it says is prepare or make ready food to make fit for eating by application of heat, as by boiling. So this is a terrible definition, because of course you cook ceviche by changing pH. You cook things by doing lots of different things. So we decided to define cooking as a plot. So we're scientists, and so scientists like to do things as plots. So we made a plot, and here is our plot of definition. So basically, you see, there's a temperature scale. That could just boil the pH or anything else. So the deal is that below a critical temperature, the food is uncooked, and above the critical temperature, the food is cooked. And cooking is essentially getting the change in phase, and you can cook by doing lots of things. We're going to cook. Some of you are going to help me cook by stirring in a little while. That also works for cooking. So, but this is an example of what scientists call a phase diagram. So I want to now do this for a minute. So let's cook some ice. So now I need to switch this. Okay, let's see if I get this right. I'm still already good here. Very good. This is where this thing's going to get exciting. So, okay, these are two hot pans. And I have here some ice. Does anybody know what happens when you cook ice? Has anyone ever cooked ice? You know it? Okay, here we go. Ready? It becomes a gas. So when you cook ice, it becomes a gas. You all knew this, right? So that's sort of boring. That's what you take physics and tell you that. Okay. So now actually watch this. So now we're going to cook an egg. Egg. Let's see. Okay, so I'm going to cook an egg. Has anyone ever cooked an egg? Watch this. What happened? It became a solid. Isn't that unbelievable? I mean, when you cook ice, it becomes a gas, but when you cook an egg, it becomes a solid. How can that be? Okay, I'm going to take this off. Anyone's interested in eating this? Can I have this? Is that a yes or no? Yes. Okay. That's hot. We'll leave that hot so we can cook some tuna. Okay, so that's so we've now done a little bit of cooking. That's good. We'll do more cooking. Don't worry. There's more than that. Okay, so right. So you know about this solid liquid gas. So we taught the students an equation that predicts when. So that was the equation that took class, right? It's a very simple equation. Some of the scientists might be appalled by it. We debated these equations, by the way, for days before we made them up. But this equation actually predicts when the temperature of a liquid becomes a gas. It actually predicts it. So scientists have enough understanding of the physics of this process that you can predict it. Now, of course, what's strange is that when you cook an egg, as we already did, it becomes a solid instead of a gas. So if you're interested in this, what you really should do then is figure out the physics. You have to find an equation, because that's what we're scientists are supposed to do, that basically captures how can it become a solid, and then when does that happen? And actually, it turns out the equation that we taught them, some of these scientists might be appalled by this, I actually think it's pretty good, was this equation. So you have to clap. It turns out the physics of egg cooking, just in case any of you are curious, is that eggs contain in them proteins. Now, of course, you know they contain proteins. I mean, if you look on the label, it says there's proteins. But the proteins, when you heat them up, they're these globby things. And when they heat them up, they unfold, and then they're really sticky, and they all stick to each other. So imagine that you all joined arms and stuck to each other. You would become a solid. That's what happens to the egg. And the game is to predict when that happens, and that's what that equation does. Oh, something burning? Sorry. Okay, let's check that we're not. The thing is that the egg is no longer being heated, so there should be no. Yeah, we're good. It's just a bit of a burned egg. It's okay. Oh, do you want me to put some water in? Oh, you think it's the other thing? Oh, you think it's the other thing?
Yeah.
No, but it's been hot the whole lecture. You just don't know. But there's only water on it. I would like to keep it hot. That's okay. Because I want to cook tuna. Maybe we'll just cook the tuna. Okay, we're going to cook the tuna. But we need a stopwatch. Does anybody have a stopwatch? Okay, I need you to do, so from one of you have two people with stopwatches. I'm going to cook one of these pieces of tuna for 1 minute and one for 3 minutes. Could you please, so one of you, the person in the front, you're going to tell me when it's 1 minute. The person in the back, you're going to tell me when it's 3 minutes. You guys ready? You guys ready? Ready, set, go. Okay, here, I'll let you watch this. It's very exciting. We're cooking tuna. See, there it is. Okay, I need the spatulas. So you have to yell out when it's 1 minute, because otherwise this whole thing isn't going to work. Right? Well, I'm making a measurement now, actually. It doesn't look like it. This is a scientific measurement. Has it been a minute yet? No. This is there's suspense here, actually. There's suspense. Actually, maybe while it's cooking, I'm going to write the equation on the blackboard that we're going to use. There's chalk here. Okay. This was one of our equations of the week. L is equal to the square root of pi dt. 47 seconds. Okay, this isn't very exciting. I'm sorry, everybody, but I have to be ready to take it off. Okay, now we're going to. So this one's the minute one. Okay, good. Okay, and then the 3 minute one, you're going to go. So you don't tell me when you promise to tell me, because otherwise the measurement will be messed up. Okay, so we're going to go back. Computer. Okay. Okay, good. So now we're going to do another cooking experiment, actually, if you don't mind. So I need 2 volunteers. 1, I need someone else. 2, you guys, come on. I need 2 volunteers. Okay, you have to get away from the stove when it's hot, because we don't want to hurt you. So here, you guys are going to go here. Okay, and this is the experiment. We're going to cook egg in a very different way. Okay, so this is your bowl and this is your bowl. You have to face the audience. Okay, has it been 3 minutes yet? Okay, so the way that this experiment is going to work is notice each person, what's your name? Noah. Okay, Noah, what's your name? Patricia. Noah and Patricia each have whisks. Now, Noah's job is going to be, this is water. So your job, when I tell you to go, you're going to whisk the water in 1 minute. Okay? Okay, now, Patricia, you, on the other hand, this is an egg. I need to do this. So I'm going to basically just put the egg white in the egg. Maybe we'll do 2 egg whites. Has it been 3 minutes yet? See, I told you. Some of you are probably better at this than I am. I think I'll give you a little more. You need a little more egg white for this experiment. Here, wait, we need to crack a couple more eggs. Hopefully it's one. Do you want to crack more? Yeah, we just want the egg white. I mean, this would actually work. This experiment would work if you had the yolk too, but. Okay, yeah, that's a good round. That's good. Okay, we're good. There are apparently paper towels. 10 seconds. 10 seconds. Okay, hold it. Where did my thing go? Go? Okay. Now, Patricia and my hands are both covered in eggs. Good. So one of the calculations that we did in class is we taught the students, I gave them the following problem on the final exam. Suppose you're making cookie dough. And suppose that you leave cookie dough on the counter overnight. And suppose you're unlucky and there's one salmonella on the cookie dough, and you leave it on the counter, and it divides over 20 minutes. How long will it take for the mass of the salmonella to be the same as the mass of the cookie dough? that was why we should wash our hands. Anyway, okay, so now these guys, the 1 minute person, I need you one more time. Are you good? 1 minute, okay. You guys start whisking. Ready, set, go. Okay. Okay, they're just going to do that for a minute. I hope it's not distracting. We're just going to let them go. So, you know, Noah's whisking water, Trisha's whisking egg. Let's see what happens. Oh, no, I can't tell you. Has anyone ever done this experiment? No, we have to wait, sorry, because the next slide gives away the answer. Let's see how we're doing. Yeah, we could have done it under that. Okay, don't steal it, because here. Okay, you're doing very well. Can you whisk a little harder? Could you whisk that a little harder? Yeah, it's hard as you can, actually. Just don't spill that whole. We're working on this. See, cooking is actually hard work. I mean, these guys are cooking. The energy has to come from someplace. Okay, so, actually, I should have had to do this under the projector, but we'll look at the result of the projector so you can see. 5 seconds. 5 seconds. Okay, I think actually we're getting there. I think that this is, maybe just do it a little more. We're going to give it a couple more seconds. Is everybody bored? Is this okay? This is okay, because I really want to make this point. It's very important. Okay, I think that's enough. I think we're good. So, no, could you please go and you can't touch the hot pan. I'd like you to pick this up and show everybody and what you did. This is cool. So please hold it up. I don't want you to hurt yourself. So very good. Go over there and show what you did. So they don't touch the hot pan. Now. You must be much better at stirring. So watch this. So we started with a liquid in both cases, and when Noah did his experiment, it ended with a liquid. But look what happened. It's a solid. I mean, it's a solid. I'm holding it up. It's not falling down. That's a solid. Isn't that bizarre? Okay, thank you guys. So now let's look at the solid under the microscope. So isn't that bizarre? When you whisk something, it becomes a solid. How can that be? This is the exciting part. You have to push the buttons. See, David is getting very happy. He loves bubbles. He's one of the world's experts in bubbles. Oh, we have lots of world experts in bubbles. This is so great. We're showing bubbles. The world experts in bubbles. But look, they're bubbles. Isn't that amazing? So it made bubbles. So actually what happened is when Patricia was whisking, apparently air was getting in there. And then it made bubbles. But when Noah was whisking, the same thing must have happened. So why didn't water make bubbles? Does anybody know? Scientists aren't allowed to answer. Lack of protein. It has to be the protein, right? The only thing. I mean, so what eggs? It's mostly water. I mean, you know we're mostly water. You know what percentage of you is water? It's like 60% or something, right? Some pretty high percent. So most of egg is water, actually. But yet, there's enough protein to stabilize bubbles. So now we actually have a new science problem, which is how is it that protein stabilizes bubbles? Okay, I want to go back to the computer. So let's go back. So this is totally bizarre. Okay, and the answer is that, and this is what it says, is that basically when you mix, you make a foam, and egg whites have in it a protein of albumin, which actually acts as a surfactant, what scientists call a surfactant, and that surfactant stabilizes foams. Now so we introduced, some of the weeks we cheated and we gave more than one equation, but this was one of our equations. We taught the students what surface tension was. That's the thing that basically, and we basically showed them, we talked about the surfactants. We had a beautiful lecture actually in the school by Kate Stebbing on Tuesday, I think it was, or maybe it was Wednesday, about surfactants and basically how they can stabilize things. So we taught that to the students, and we told them about surface energy. Now, it's literally a fact that this person gave a lecture not 3 hours ago when she wrote that equation on the board. Isn't it true?
No, I forgot the 4 pi.
He forgot the 4 pi. But yet we taught this to the students, and we even told the students, we even told the students we even talked about the pressure too. We talked about all of these formulas, and then we made them use it. I'll tell you that a little while. So okay, so the last science topic I have. So the last science topic we have is spherification. I'm going to do this very quickly. So this is actually one of his greatest creations. So I'm going to show this to you as a movie, and this is so that there's at least some fancy cooking in this because we promise fancy cooking. So I'm going to show you a movie. Hopefully it will work. I don't really know. Let's see if I can. Here we go. So Ferron, this is spherification. And so this is a DVD from Ferron. And I'm going to show you Ferron's creation of spherical peas. If the computer works. he ground up peas into a liquid, you saw that. But then he made a shell around it that was a solid. And so there was a solid shell, inside the solid shell was peas, and when you bite it, it's the most intense pea taste you will ever have. And actually, if you're interested, if anyone's interested in this, after this I have a video, I have like billions of addresses. You can see it for hours and watch these things, of the things you can do. But anyway, okay, so what's the science? So basically what he did is, remember, we already talked about eggs. And we talked about there were proteins in the eggs, and the proteins unfold, they stuck to each other. So how are you going to do this? So you somehow have to put something which causes what scientists call gelation, namely the sticking together of proteins actually together into the peas. And what Ferron did was to add a polymer in this at some point, which is called alginate. This is a perfectly naturally occurring polymer that actually is in seaweed. And it turns out that alginate is a negatively charged molecule that if you then put calcium in, calcium is a divalent ion, that means it has two positive charges. If you have two positive charges, positive and negative charges like each other, and if you have two negative charges and one with two positive charges, they stick together, and it actually sticks the gel together. So to basically make it so that it becomes a solid, and it does it only over the outside of the thing. Now, this is now going a little beyond. So the equation of the week this week, when we did spherification, one of the equations actually has to do with elasticity, but the other one, which was really very beautiful, I think, is exactly, it turns out the thickness of the shell that occurs around this thing is exactly the same equations that I wrote down over there, which we're now going to use to measure the diffusion constant of heat. So actually, the equations, and the scientists in the room all know this, the same equations come up again and again and again. But actually, in cooking, it really does happen. So now, what I'd like to do is, I want to finish, and then we'll go, we're getting to the end. I have a little bit more, but I want to now do the measurement on the tuna steak that we cooked. So I need a volunteer, because I don't want anyone to think I'm cheating. Would anyone like to? Could you help me for a second, please? Because I don't want anyone, I mean, this may not work, it's like all things. So the scientists, so you see, we have these tuna steaks. And you'll notice, do you agree that part of it is white and part of it is pink? So what I'd like to do, actually, if it's okay, is measure the thickness of the white layers on both of these two things. So could you help me? This is a ruler. So if you could just measure and did that, and that one, just sort of tell me what you think, just how far the white goes in. And I'm just going to have her do it, because otherwise I just don't want to. You might think I cooked the answers. This is actually about, this is so it went up about where? So it went up there, okay, right there. So that's actually half a centimeter. Is that what you're supposed No, it's about that's a half a centimeter. Okay, and what about this one? So what about this one? Where does that one? Okay, about one. Okay, thank you. Very good. Okay, so we have two measurements. We did 1 minute, which is equal to 60 seconds. And L, the thickness of the white layer was, what did we say? We said it was half a centimeter. Half a centimeter. Okay, so, and now what we want to solve for is D. D is a fundamental property we have, which people measure in physics classes in much more boring ways than this. So for those of you who remember a little bit of math, actually instead of a pi here, I'm going to put a 4. I don't want it. It doesn't really matter. The B doesn't really matter. This is all the same. Actually, 4 is probably a little more accurate than pi. For some reason, we're just the class I know. I don't know. Anyway, L squared over 4t. Okay, so let's do this. So this is 60 seconds. So L squared. So 1/2 squared. So 1/2 squared, centimeters squared, over, and we have to divide by 60, and then times 4 seconds. So that is 1/4, that's 1/16. Does anybody know what 16 times 6 is? It's about 100. So that's about 100, this is 10, oh no, we should get the actual number.
96.
We've been having this argument in this meeting about whether numbers are important. 8. This is 1 over 480. Is this right?
Yeah.
Is this right? Centimeters squared per second. Is that right? 4. Oh, this is wrong. See, I can't. Does anybody know what this is? Does anybody have it? Must have these iPhones. What is it? 960. And what's 1 over 960? No, 1 over. It's about 10 to the minus 3. So this is 10 to the minus 3 centimeters squared per second. So actually, the actual diffusion constant of heat turns out to be about 1.4 times 10 to the minus 3 centimeters per second. So you just measured diffusion constant heat. And the students actually all measured diffusion constant heat in this class by putting their chocolate chips. Oh, let's go on. We can go back and check. The second measurement should work too. But I don't want to keep everybody too long. I just go on with this. Oh, we also talked about that equation, by the way, for the scientists room. This is about the elastic envelope. And so I know we started 10 minutes later, so I still have about 10 minutes. So I'm okay. So I now want to go back. So this was science cooking. So, okay, so and I could, as this about after go on. I mean, there's so much science cooking you wouldn't imagine, and hopefully this is giving you some flavor of this. So, but remember, the reason we did this, the reason that basically I devoted my life to this for 6 months entirely, was that we were trying to figure out if this was a good way to teach science. And so there's an interesting question actually of how do you know if you. I mean, I actually don't know the answer to this. How do you know if you taught anybody anything? And we actually, for various reasons, when putting this class together, decided that the class had to be very hard. That in terms of its technical difficulty, it had to be harder than most science classes for history majors, because otherwise, the worst thing that could ever happen is we would have taught a cooking class, and the students would have gotten physics credit for a cooking class, but we didn't teach them any physics. So we tried to basically make the class a lot of work. And there was a midterm, there was homework every week, there was a midterm, but then there was a final project and a final exam. What I now want to do is just go through and tell you a little bit about the final project and final exam, just tell you about what the students did and what sorts of questions we asked, and then we can stop. So the final projects, actually, every student, the semester ended in December. The science fair was actually on December 7th. We had a science fair, and every student had to, in groups of, either by themselves or in groups of 2 to 3, carry out a science project on science and cooking. And we gave them help. Actually, some of the fancy chefs, both internationally and locally, suggested questions that they might investigate. And we then had a science fair. This is actually the same picture that was on the poster of this thing, and it was on the cover of the program for the science fair. And we had a science fair in which the students were presented their work. And because this whole thing that I told you about was completely over the top, we made the science fair over the top too. And so we sort of ran Top Chef. But it was a very different type of Top Chef. That is, the students, so we assembled a panel of judges. The panel of judges included, this is Doug, he's the executive chef of the Boston Red Sox, sort of the executive chef from Harvard. And then we had chefs from actually all over the world. So from W50, people came from Spain, David Chang came from Momofuku, Harold McGee came back actually. And these were the judges in the science fair. We put a couple of scientists on the judging panel, and then what happened was the students basically were competing in the science fair. And so there were prizes. And the grand prize, and this is completely over the top, and this actually was Farron's idea, and this happened, is the grand prize winners won a trip to El Bulli. Which the students went on June 1st or something, and it's closing on July 31st. And they also spent several weeks doing science and cooking actually with the Farron's organization. So they actually learned a lot as well. Then, Nookie actually got the Red Sox to donate both tickets to batting practice, very good seats, and dinner in the executive dining room. And then we had all these local restaurants donating things. And so we had all these prizes. So the students were extremely motivated. Anyway, so I can describe to you, I'll describe to you a little bit about what happened. So Harvard made a video of this, and they actually, I think, did a good job capturing the spirit. So I'm going to...
Reached what I call a critical temperature. And then 2%, it's about maybe 66 degrees Celsius. It reaches that temperature, and then if you keep heating the microwave, and keep heating the microwave, the temperature doesn't rise. It's kind of like when you think about you're boiling water, you can't get it above 100 until it happens.
I am the chef and owner of Oleana in Cambridge, and Sofra in Cambridge, and my husband is the farmer at Sienna Farms. I think there's a lot of inspiration, a lot of ideas behind things that could change for the good. Combining the two, and I think that the creativity combined with the science is what it's all about.
For what that last year contaminates, you would have felt that they don't have done for 4 hours, there was less bonding. It's more liquidy, it's a little soft.
Matt Menendez, I'm a freshman. My family's been in the restaurant business for generations. My dad has owned a restaurant for like 35 years, so I work in the restaurant a lot. It's sort of the family business, and I've always been interested in food. This is the kind of science class I knew that I wouldn't have if I went anywhere else. My dad was finding out about this as it was announced back in March of last year, and so I actually heard about this before I made my college decision. And it's not like it changed my decision, but it was one of those things where I said, wow, this is something you'd only get in Harvard. I think it's fascinating. It's like, I couldn't have any other science course that I would like more than food and science.
They were just sitting around, maybe, they know that the enzymes matter in it, and I think they haven't even attempted, they could try whey protein powder, and it could become different. I mean, they've only used one type of gelatin. The other thing was they only had gelatin powder.
My name is Erica Seidel, and I'm class of 2012. I'm a science concentrator to begin with, and so coming into this class, I was beyond excited. I'm also a huge foodie. So just the idea that you can learn something that you're already really interested in and apply another topic that you wouldn't really typically think would be as related as, say, spring constants, but just taking constant and doing the same kinds of things with that was just so exciting.
I'm not going to tell you what the students who won did, because that's sort of too easy in a way. So Nathaniel was one of the people who won. But I'm going to show you a couple of the projects that the students did that didn't win, and I guess it's hard to basically measure this. This is not data, so I don't actually really know what to say about this, but there was a very deep bench. There were very many projects like this. These were not randomly selected that I'm going to show you, but on the other hand, there were a lot that were of this quality. So these guys actually, it turns out that David Chang, who owns Momofuku in New York, had made a pork bushi in which he had basically taken pork and thrown it into a bowl of rice and just let it sit there. And then apparently, I don't actually know why this was. There were people apparently eat it if they like it or something. But he didn't know it was in there because he just let it sit there. And so these guys, basically got a sample of his pork bushi. And the undergraduates actually had access to scientific equipment. Harvard actually has this wonderful policy that if I wanted to sequence DNA, I have to pay a lot of money, but if an undergraduate does, it's for free. And so they sequenced the DNA that was in the pork bushi, and they discovered a new species of bacteria. So this is Brittany. So Brittany basically, so we had a rotovap in the lab. We had all this stuff in the lab. A rotovap is a thing that you basically eat something up and you then collect and condense the vapor. And Brittany basically had this brilliant idea. She was interested in peanut allergies, and she went and read about peanut allergies and discovered that actually the reason that people have peanut allergies is because of a protein that is in peanuts. And so she then basically took the peanuts and put them in the rotovap. She heated it up, and she collected the condensate. We told them that flavor molecules would tend to be small molecules and were less more volatile. That's why you probably still smell tuna. Because flavor molecules are small. She collected the condensate. She then went and took it and put it in a measuring device and measured the protein concentration and discovered it was down by a factor of 10,000. So she made what she called peanut flavor without peanut allergies. So this is Amanda. So actually it turns out one of the sort of sad things about scientific cooking, at least for me, is that the most important reaction is called the Maillard reaction. It's the browning reaction. It's the thing that you smell. It's the single reaction that leads to almost all flavor molecules. So this is why if you take a steak and you put it in boiling water, then it tastes terrible, right? Even if you put it at the right temperature, if you then brown it, then all of a sudden it tastes good because you're releasing the flavor molecules. These are called browning reactions. And it turns out browning reactions are very complicated. They're not really very well understood. I mean, there are things about them that are understood. Like, for example, I don't know if you knew this, but if you basically brown onions, so here's an experiment for you to try at home. If you go home and brown onions, and you put in one hand onions, the other hand you put onions, put a little bit of baking soda in it, the browning reaction accelerates enormously. You'll see it's an amazing effect. And it's because one of the steps of the browning reaction is pH sensitive. It actually accelerates with basic reactions. And it's sort of understood why, but it's very hard to quantify. For that reason, we had a very hard time teaching this stuff to the kids. I gave this lesson really terrible about the browning reaction, so I didn't know what to say. Anyway, Ashley and her team figured out how to quantify the browning reaction. This is what they did. They cooked potatoes. And then they took photographs of the potatoes as they were cooking. And then they put them in Photoshop. And they measured the brown color as a function of time. And they showed that it had a pH sensitivity, and that it basically corresponded to the time of the browning reaction. So this is going to become a lab. So this is Greer and Michael. So Greer actually is an avid reader of the New York Times recipe section. She found a recipe where you could make ice cream using not eggs but vodka. And she wondered why. And so she then made eggs. They made ice cream using both eggs and vodka, put it under the microscope, you see the pictures, and tried to figure out, and actually did figure out molecularly why you can stabilize bubbles actually using vodka. These guys made unmeltable chocolate. They made chocolate that doesn't melt at 100 degrees Celsius. Their recipe basically then had a ravioli. They made a ravioli in which the outside of the ravioli was made out of their unmeltable chocolate, and in the inside they put actual chocolate, and then they cooked it. And so it was unmeltable chocolate, so they had chocolate ravioli with chocolate on the inside. Their only problem was the chocolate didn't actually taste that good. And actually, I should say, for scientists, the rheology of this chocolate was fascinating. And these guys, so Dave's lab, poor Dave, basically his lab was taken over basically for weeks with these students basically making rheology measurements. If you see a dip in productivity in Dave's lab, all the scientists out there, it's because the students were all using the equipment for several weeks. So these guys, actually, why are you afraid of WD-50? I told you he made shrimp noodles, so he was interested also in making Parmesan noodles, as he wanted to make noodles purely out of Parmesan. He did this basically by using an enzyme called transglutaminase, which cross-links shrimp, and tried to do it with Parmesan noodles. He wasn't able to do it. And so they basically presented the problem to class. These guys took it out. They solved the problem in about a week. And actually, I think it's now going on the menu. Okay, so that was the science class. We could go on. We could do this if we have time. We could go on. But I'm happy to talk more. There was a group that made guacamole that didn't brown. So the way they did it is it turns out that the browning reaction in guacamole and avocado is caused by a protein, but when the protein when proteins heat, they denature. The team wondered if you heat it, then maybe you'll get rid of the oxidation reaction. If you do this in boiling water, people have tried that before, of course, but then what happens is that you also mess up the texture of the avocado. But we have these constant temperature heat baths. So they found a temperature where you didn't mess up the texture of the avocado, but that you unfolded the proteins and thus it didn't brown. Okay, so this was our final exam. This is really the very end. So this was our final exam. I'm going to just give you a couple of questions on our final exam, because I want to just give you a flavor of what we did. So this was my favorite problem, actually, in the class. So it turns out I told the students on the first day of the class that I only knew how to cook one thing, which is chocolate chip cookies. And then I was very pleased that the third of the final exam was then about Nestle Toll House chocolate chip cookie recipe. And so I just want to tell you the sorts of questions that we asked. So we gave them the recipe. We gave them the ingredients in grams. This is important if you want to ask scientific questions, because weight is a better measure of the volume. Here are the questions. So during baking, much of the water content of the cookie dough is lost. Hypothetically, if the interaction energy between the water molecules were 8 kilojoules per mole, what would the boiling temperature be? 2, taking into account all the ingredients in the chocolate chips, calculate the total energy content of the chocolate chips, and please express your answer in joules. Number 3, in an effort to make cookies of uniform thickness, you decide to use your coffee cup to press the dough. Suppose the cup weighs 100 grams. You notice that if you shape the dough into a cube, 3 centimeters on the side, and put the cup on it, the dough compresses to 3/4 of its original height. What is the elastic modulus of the dough? Number 4, from your calculation of the elastic modulus in problem 3, calculate the distance between the cross links in the gluten network. Number 5, you place the cookies on a pan and place it in the oven according to the recipe. Approximating the dough as a sphere of radius 2 centimeters and assume that it doesn't change shape while baking. Also assume that heat is supplied uniformly from all sides. What temperature does the center of the cookie reach? Question number 6. After eating the cookies, you decide to make brownies, so you remake the dough and use it in a different pan. Assuming the heat is coming from all sides, how long should you cook these so that the temperature achieves the same target that you got in number 5? Then there's the salmonella question I already told you. And then, undeterred, you decide to remake the recipe into pancakes. Instead of butter, you use milk. Now the batter is a liquid and it flows, but the batter flows differently than the milk. Is the viscosity bigger than or smaller than it? Please give a micro argument why. So, okay, so this was the final exam. So now what, actually, so do you want to guess? I mean, I'm not sure I was supposed to judge this, but do you know what the mean on this final exam was? And I guess I should make sure that's good. So this was a population of history major. As most of the people, there were science majors in the class, but it was the minority. So the mean on this exam was 90%.
How much?
90%.
9?
And the teaching fellows, who were all scientists, graded hard. That is, they took off points for lack of significant figures. They took off points for everything you could possibly imagine because they felt that, damn it, it's a science class. So okay. Oh, right, actually, okay. So this is sort of finding out. So, okay. So, what is cooking? Something involving food is one of the following equations involved.
As anticipated, it was going to be an exciting talk, and Michael truly delivered. You guys learned about cooking and from science. So
and there's eggs out there.
Yeah. Feel free. So maybe we have some time for questions. No questions?
What was the reaction to gelatin being put in pineapple juice?
Oh, good. Okay, so it turns out that if you put gelatin in pineapple juice, so pineapple contains an enzyme which actually denatures gelatin. The enzyme is called, is it bromelain? It's bromelain. And so we did an experiment where we basically, because we were trying to teach the students that there were components in food that were really interesting scientifically. So if you take chunks of gelatin, which we dyed blue, and you put them into pineapple juice that you get from a pineapple, that is, you actually grind it, then actually you see it dissolve. But we then contrasted that with pasteurized pineapple juice. So when you pasteurize pineapple juice, you heat it up to a temperature, this is the store-bought stuff, and you actually unfold the protein and it loses its activity and it no longer dissolves the gelatin. So that was one of our first experiments. So just to demonstrate that there are interesting things in food that you really you think about it. Yeah.
I'm interested in something that you didn't quite cover tonight, but astonished me if it would be fun for the students and challenging and interesting to those who are bright and excited about energy transfer. I believe that cooking is a pretty inefficient process, and the heat transfer between, for example, the top of the electric stove and pan, which is, I guess, primarily conductive, but also radiated and put back into the electric. and the pan has been warped, and it's a little bit circular instead of been flat.
Right.
And
So,
the second, the pans themselves, it strikes me that an awful lot of the heat that comes into the pan perhaps has very little to do with
Yep. This is
the
what.
brass insulation.
Right. Okay, good. So let me answer this in two ways. So number one, what I described to you is the way that we did this. There were many other ways that you could do this, and there are many other things that you could emphasize. Because of the pace that we were on and the type of class that it was, there were lots of things that we couldn't do in as much depth as we wanted. And the depth that you're describing, we have the students read on food and cooking. There's a very nice chapter on food and cooking on everything that you just said and discussing it in qualitative terms. And they read that, and we did have some questions. We also had two. So what you just described in the class was covered by these two equations. So there was an equation for heating, and there was an equation which is basically that equation. And so we talked on that. We did sort of tell them about pans, and we mentioned that you also have to heat the pan and things like this, but we didn't really go more deeply into it than that. I mean, if this were actually a class for science majors, then, for example, one could spend several weeks on this and go into great detail into all
I
of it.
regard it as a social problem that we all face.
What you mean, the heating or the?
No, I think that the fact is that, we can make furnaces that are getting to be 5% efficient, but we cook at about 50%.
No, that's true. No, I think this is all is true. These are great ideas of what we can do, but this is how we.
I think, of course,
No, I wasn't taking it as it. I was just saying that there are other ways.
Given the success, is this going to become a permanent course?
So actually, is this going to go permanent? So the deal is that I'm now on sabbatical. Dave is teaching class. My colleague is teaching the class this year. There's a lot of energy because of this, and so we have a similar roster of chefs, and the class will happen again. And so, to the extent that there's interest, then I think there will. So we found this to be a very effective way of teaching science. I don't exactly know how we're supposed to document that. That's one of the things that I'm a little confused about, but just even capturing interest. So, sure. It's fun to teach too. I never had to cook before.
There's a question.
I have a question.
Yeah.
No, go
Yeah.
ahead.
Really the only chef here.
Are you a chef?
Is there anyone else who's a chef?
So he can tell you all the things I did wrong. You guys-
It's on the way down there.
I just kind of find that fascinating. I don't want to know the rest of you. Alcohol saute pans actually address the question you were referring to. So you notice like chemical reactions occur when you use copper bowls, when you're making certain things, what you heat things in. We got into when you're storing diced tomatoes in place called citric and background, these plastic metals, it's not just with easier to actually start to break down things like cucumbers, tomatoes, avocados, stuff like that. Simply be more exposed to them. So for that.
So, can I just make a comment about this? So this is actually very interesting, so I'm glad that you explained it. So one of the things that I was, because as I said, I don't know how to cook, as I'm sure I just demonstrated to you in very brutal terms. But one of the things that was very striking to all of us, actually none of us, Dave also doesn't know how to cook. The students knew a little bit, although they don't know, they're not really chefs. That is the teaching fellows, this teaching staff did, is we were struck by how similar scientists and chefs are. And actually the chefs that came were also struck by this, because we're all doing experimental things. Right, and it's just the sort of the notion, at some point we sort of boiled it down and we told students that, the point of science, if you're going to be a professional scientist in life, then what you should do is fail often and fail frequently. And it's more or less the same thing with cooking. And it was just so striking, because as soon as you realize, yeah, it's all experiment, and it sort of makes perfect sense, but somehow it never, I think to any of us, that is the chefs or the scientists, we didn't understand this until we...
One actual question for you. What would you say in your mind is the big
What did you say?
Anyway, I was going to ask, what in your mind is the difference between the Maillard reaction and the Maillard reaction and caramelization?
So the Maillard reaction and caramelization are both browning reactions. There are different, the chemicals that are involved, the detailed compounds, and saying, they occur at slightly different temperatures, right? That is, in the Maillard reaction, you have to heat things.
It depends on the pressure.
And it depends on the pressure. So, but they're different chemical reactions. So that's actually about the limit of my knowledge of the subject. That and the onions thing.
There's a major difference I noticed. This Maillard reaction is only with meat.
Yes.
You were mentioning Maillard reaction
Yes.
earlier with potatoes. I disagree. I would say that's caramelization.
Okay, fine.
Because
That's fine. I'm willing to agree. That's fine. That's fine.
I have a question right here.
Yeah, just for the purpose of thinking of developing a simpler course like this, I'm wondering, since you had a preparation time between May and August, what kind of institutional support did you get? There was some training for students, maybe release time for you, stipends for the chefs, or did they come for free?
I'm not sure how much of this I want to answer while So, okay, I'll just tell you. Okay, so basically, okay, so you asked a lot of questions. So we actually, the teaching fellows, once the course was announced, there were lots of graduate students who wanted to be teaching fellows. We told all the ones that if they wanted to do it, we had no idea the course was going to be this big. We had no idea. That if they wanted to do it, be guaranteed to do it, they had to start working on preparation in May, and we were all going to do it for free. So we all did it for free. We all did it for free. I actually taught this as an extra class. And this took up my entire life, basically. I mean, I'm not kidding. I lived for this semester. This was it. The logistical chapter, just everything. I mean, everybody that was on that list took up our whole life. So really, there was and we worked constantly on it. And it really happened because somehow it was one of these ideas, and it just started going, and there were all of these enthusiastic people, and then we just started running, and then we ran out of inertia and it collapsed. So that's basically, so institutionally, I don't know about that. So that didn't happen really. I mean, although Harvard, anyway, okay, enough of that. So in terms of how the class was funded, so funding was also an interesting question. We actually raised money for the class. The way that we raised money is that, and this is probably a useful thing to say if any of you are interested in this, is that we had the chefs came on Tuesdays. Every Monday night we had a public lecture series, much like this one, where either Dave or I and the chef that was visiting would get up and talk. And we basically had sponsors of that lecture series. They're all on YouTube. You can go and watch. If you go and watch, you'll notice at the very beginning, we list all of the sponsors. And that was the way we raised a significant amount of money for the class from that. And then we had donations. And then Harvard paid some too. So it was, but this was really, we just winged it. If we thought about it too much, we never would have done it.
Other questions?
I'm curious, did you take a poll of how many people were, if you converted anybody to being a science major because of this class?
Right, okay, so that's actually a good question. So, okay, so first of all, the first comment I would make is it's not clear that that's what the goal is. I mean, honestly, it's not clear that that's what the goal is. I can tell you anecdotal stories, I think, again. I'll give you my favorite anecdotal story since you asked. So one of the students in the class who was a novelist, and is an English major, she basically told me the following story. She went home after the class for Christmas, and her mother was making lasagna, and she made much more lasagna. Their pan was much bigger than the pan of the recipe, and she didn't know how long to cook it for, so Isabel calculated the cooking time. So to me, that was, you would even think to use an equation.
Final question, maybe?
This is not a question, but an anecdote. 68 years ago, the final exam in differential equations was how long will it take a block of ice to melt?
Probably you expected a more rigorous answer than the one that we did. But as the dean will tell you, it's only a factor of a couple of those off between the two answers.
68 years ago.
Okay, maybe on that note, thank Michael again. If you have other questions.